Hello, everybody. I hope you're all enjoying the conference so far. Welcome to my talk, which is on zero downtime live migration for stateful workloads on Kubernetes and beyond. We're gonna go into that a little bit later. That title is obviously a little bit of a mouthful, but it's actually exactly what we're going to try and achieve today, which is a grand and historically impossible goal. Can we take any stateful application, right? Think Redis or Postgres, running on a Kubernetes cluster somewhere and migrate it between the nodes. And this needs to be a zero downtime migration, right? So the app has to stay alive the whole time. 1 second, your app is running on node A, and the next it's on node B. It just magically moves and keeps running. You're not shutting down and restarting it somewhere else. In fact, the app shouldn't be able to tell that it's moved at all, and clients shouldn't be able to tell that it's moved. And speaking of clients, if we really want to have some fun with it, can we keep the network alive while we do the migration? And then, as if all of that wasn't enough, can we do it anywhere? So between regions, between cloud providers, or if we're really going to go all the way, then between continents. Okay, so that's a very lofty goal, and we didn't really set ourselves a lot of restrictions. We're basically saying, can I take any application, right? Because if you can move stateful apps, you can move stateless apps, right? So any application that's running anywhere and move it so that it's magically and instantly running somewhere else. So any application from anywhere to anywhere. And I mean that without restrictions. And, we call this the proverbial, holy grail of infrastructure. Can that be done? You actually wouldn't think so, and in fact, most people consider this to be an impossible problem. And up until today, they'd actually be right. Live migration has existed for years now as part of various virtualization layers. VMware was actually one of the first to come up with this as part of vMotion back in 2003. That was 21 years ago at this point. In 2007, support was added to KVM, and today there are even user space process migration solutions like CRIU that don't depend on any specific hypervisor. Unfortunately, all of these so-called solutions come with massive caveats, most often in the form of downtime. With QEMU, which is a front end for KVM, applications can suffer from serious performance degradation during a live migration, which itself can take a really long time to complete. Not to mention the fact that the live migration can cause multiple seconds of downtime and will often just fail outright. Oh, and it doesn't do anything about the network for you. The IP address will change and clients will get disconnected. Now, VMware is actually slightly better. It will actually migrate the network for you, as long as you have complete control over the computing and networking hardware, have node-to-node latencies less than 10 milliseconds, high bandwidth connections between your nodes, and have deployed a very bespoke networking topology, which is something that's often only possible if you're just migrating within the data center. Not to mention the fact that even after all that work, you have to lock yourself into their very expensive ecosystem. So it's an impossible problem, not because we can't do the live migrations, but because they're not really practical or even all that useful, thanks to all of those restrictions. Cloud providers actually allow you to migrate VMs between availability zones today, but only between availability zones in the same region. They actually buy land for their data centers so that they're less than 5 or 10 milliseconds apart, so that they can support this use case. And even then, with all of that work, your migrations will fail if your application is under heavy load. This is a very real, very common issue, especially on GCP. So not any application, not from anywhere, and not to anywhere. Not until now, anyway. So I should explain who I am first. My name is Shivansh Vij, and I'm the founder of a startup called Loophole Labs. This is my Twitter, Confused Qubit. You can hit me up there if you have any questions after this talk, or you just want to, chat. And then there's my GitHub and LinkedIn, which are both just my full name, Shivansh Vij. These are our socials for Loophole Labs if you want to follow along with what we're building or get in touch with us after the talk. Okay, so at Loophole, we have been searching for this holy grail for a while now. And we've always imagined a world where you would just be able to move an app without restrictions, without downtime, to anywhere you wanted. Let's assume for a moment that I'm telling the truth. Just, grant me that. I'll back up that claim in a moment. But for now, what happens if today it's really possible that you can do all of this? What can you build with it? Well, right off the bat, you can build services that can migrate themselves around to achieve the lowest latency for all of their connected clients. For example, let's take a Zoom instance, right? Let's say we have a user in San Francisco and then another user maybe here in Austin. We'll start our Zoom instance in Chicago because maybe we already have a warm instance there. Then after the call has started, we can determine that Denver is actually the best place for this instance. That's the data center that's going to best minimize the latency between our participants. So the Zoom instance just moves itself over to Denver without interrupting the call. Now imagine doing this with a matchmaking server for a video game or a database with a bunch of connected clients. Do you see what I mean? It immediately changes the way that you think about distributed systems. Now, let's shift gears for a second and talk about the economic benefits of all of this. For one, we only need to spin up replicas in one region, maybe our most popular region, and then move them around the world to take on load as it appears. So fewer global replicas. And, that's obviously much, much more efficient than the current state of things. And speaking of efficiency, you can throw away bin packing completely. You don't need to find the optimal way to pack your workloads onto a host. Just start them wherever and then continuously migrate them between the nodes to always have the optimal packing. Heck, you could even use spot instances for all of your stateful workloads. Let's take a second and think about that. On EC2, spot instances are 90% cheaper than on-demand instances without any contracts. But in return, they can be taken away with a 2-minute warning. So you can't really run any sort of stateful workload on it, nothing like Postgres or Redis. But what if you could get that 2-minute notice and just migrate away? No downtime, no disconnected clients, no drop packets. Why would you ever use anything else? And that's what's at stake here. The entire modern paradigm of cloud infrastructure is built on not being able to do this. And now that you can, disaster recovery becomes trivial. And so does data compliance. Your compute can move to your data instead of the other way around. Cloud lock-in disappears, and in fact, multi-cloud becomes the default. And what I mean by that is, let's say, those spot instances that I mentioned a second ago, you can now run your stateful workloads on the cheapest spot instance, in the cheapest region, on the cheapest cloud at any given time. So that's what we've been chasing at Loophole. So I've said a lot of very grandiose things, right? And I'm telling you that as of today, we can do all of this cool stuff. And hopefully I've gotten everybody at least a little bit excited. But now I need to back up my claim. And as part of that, I'd like everybody to download Minecraft, the official Minecraft client if you're able to, specifically version 1.12.2. I thought it'd be fun to get some audience participation for our live demos in the talk. And, what's more fun than Minecraft? Okay, awesome. So now we can talk about how all of this works. And to do that, let's first take a look at how we orchestrate stateful workloads today. And specifically, let's look at containers and Kubernetes. We'll talk about VMs in a bit later in the talk. So how do you run a stateful application on Kubernetes? Well, the application part is easy. That's just a Docker container. The stateful part is what's important here. How do you maintain state on Kubernetes, especially since our pods are ephemeral? And this is where Kubernetes' dirty secret comes into play, which is, of course, persistent volumes. And the way persistent volumes works is actually quite clever. When you have a stateful application on Kubernetes, because your pods can go away at any time, and that's kind of how you want to design your apps, you use a persistent volume to store all of your state. Let's say your pod wants some sort of storage, so it makes a claim on a persistent volume claim, if you will. The PVC then tells Kubernetes to mount or connect a volume to that pod. And the PV itself is backed by some sort of real storage, right? So Amazon's EBS or Azure Disk. So your pod can write to the persistent volume via their PVC. If your pod gets destroyed and recreated somewhere else, it just binds to the original volume that the original pod was using. So while the pods themselves are ephemeral, the volumes act as persistent data. Here's the thing though. Persistent volumes do nothing to help you avoid downtime. They just give you a false sense of security. At best, they might help you prevent data loss by pushing persistent state onto a disk. But if your pod gets deleted or your node goes down, your clients will still get disconnected and you will absolutely have downtime. And now, on top of that, any state that you hadn't flushed to the disk will be lost. So persistent volumes can't really help us with live migration, right? That's not completely true. There is actually a really important exception to this, and that's something called application layer replication. Now, this talk is about migrating arbitrary stateful workloads, things like virtual machines or containers. But as we said, that hasn't really existed before. So at Loophole, we needed a starting off point. So we decided to look at applications that could already achieve some sort of zero downtime live migration in various forms. And specifically, we looked at transactional databases. Transactional databases like Postgres allow users to replicate their data to different nodes. And clients can just connect to whatever node they want, usually the node that's closest to them. When a database transaction occurs, it gets replicated to all of the nodes in the cluster, meaning any copy of the Postgres database can answer any query. This is a common technique used today, and with application layer replication, we can not only prevent our data loss when the node goes away, but if we could somehow route clients to a different instance, we could achieve true zero downtime live migration. And we could do it on Kubernetes. In fact, let's actually try to implement this. Instead of doing a Postgres database, let's start with something a little bit simpler, like a to-do list application, right? We're going to start it on a pod here on node A. And we'll set things up so that the to-do list server is writing its persistent state to a connected volume. Okay, so whenever we want to add an item to our to-do list, we write to the volume, and of course we can read the contents of our list directly from that volume as well. Now, next, it's important that we deploy an application protocol aware router between the Kubernetes nodes and our client. So our client is going to connect to our HTTP router, because that's the application protocol, and we'll send all of our read and write requests to that. Then our router will forward those requests to the correct Kubernetes node. In our case, that's going to be node A. So now, if you want to add an item to our to-do list, that HTTP request leaves the client and it goes first to the router, which then sends it to node A. Then our server writes that item to the volume. So now let's say we want to migrate our application to node B. And because this is a super important to-do list app, we want a zero downtime live migration. The client should actually always be able to access the to-do list, both modifications and just reading. So the first thing we're going to do is spin up a replica of our pod on node B. And we'll set it up so our replica also mounts the same volume, but we're not going to write anything to it yet because our new pod isn't serving any requests yet. Next, once everything is mounted up and working, we'll instruct our HTTP router to forward all future requests to node B instead of node A. So the next request, be it a read or a write, will get sent to node B, and our server running on node B will interact with the same volume that the server on node A was interacting with. So it'll respond with the exact same correct data. And finally, we can just clean things up by deleting our old pod. And with that, we actually have a legitimate zero downtime live migration. And we actually kept the network alive the whole time. Unfortunately, we're still missing some very key things. Most important is the fact that this isn't really application layer replication. We're just mounting the disk in two places. It's great for this example, but it's completely impractical if our nodes have any sort of latency between them, like if they're not in the same data center, not to mention the fact that we're relying on this magical disk infrastructure that can mount in two places at once. It's funny, actually, because this magic disk infrastructure is actually a requirement for modern live migration techniques. If you've got a disk full of data, modern live migration will just move the VM's memory around, but it'll still require you to mount the original disk in both places. With all that being said, we do have a good starting point. We just need to tweak it a little bit. So let's first begin by making a couple of changes. Let's start by getting rid of the shared persistent volume. We can't rely on that existing. So let's give each pod its own persistent volume on node A. Now we'll set up our application so that our to-do list server still writes to its volume, and specifically it writes to a log file which keeps track of the current state of the to-do list. Now with this setup, how would we do a migration? Well, let's start the same way as before. Let's spin up a replica on node B, again, with its own persistent volume and with its own log file, right? Next, we'll begin by replicating our log file from node A, which, remember, contains the current state of the to-do list. We'll push those contents to the log file on node B. And of course, we're going to have to build some sort of custom protocol for this, right? A to-do list aware replication algorithm, so that we can actually push those changes. And we'll also have to modify our to-do list server so that those changes are only pushed to the other node after that so that we only acknowledge writes after we've pushed the changes to the other nodes, right? So that way we know we've always successfully replicated the log to node B. And just like before, to actually do the cutover, we just tell our HTTP router to forward all future requests to node B instead of node A. And again, to clean up, we just delete everything on node A. In fact, we can just delete node A altogether now, right? Look at that. We just used application layer replication to do a zero downtime live migration. And as promised, we still kept the network alive. Unfortunately, there are still some major issues with all of this. And the core of all these issues is that none of this is really practical at any sort of scale. For one thing, our application has to be designed for replication from the very beginning. We have to know that we're going to want to do the migrations. We have to make sure that we can push all of the necessary state to the log file. And then on top of that, we need to come up with a very bespoke replication algorithm. And as you can imagine, that's both extremely difficult to get right and a lot of work to maintain. Our client protocol now has to be transactional. We have to make sure that our server replicates the log before it returns a success. And if our nodes are really far apart, that means our to-do list is now super slow because each write has to get replicated to all of the different servers. Speaking of clients, we now have to make sure our client protocol is supported by our router. It seemed super easy here because we were just using HTTP and we can just send the next HTTP request to node B. But what happens if we want to do any arbitrary TCP or UDP application, like, Postgres or Redis or even Minecraft? We also haven't really talked about what happens if the latency between our nodes is too high or the bandwidth is too low to actually send the replicated data in a timely manner, or how we synchronize this entire process with the HTTP router and Kubernetes. We've glossed over a lot of details. But we've also proven that it is possible. And at Loophole, we have a saying, which is that all we need is possible, the rest is just an implementation detail. And in our case, that implementation detail consists of somehow applying these techniques to arbitrary stateful workloads, like VMs. Remember, we said it wasn't practical because we'd have to come up with this process over and over again for each new application, and it wouldn't work on existing applications that didn't already implement replication. But if we could somehow replicate any process or any VM, then we only have to implement it once, and we only have to get it right once. Practically, we also have to make sure the replication process is a lot better than what we just described so that we can actually get those instant migrations in scenarios where there's high latency or your application is under heavy load. And of course, we also have to figure out how to move raw TCP and UDP connections around. But let's ignore those issues for a second. Like I said before, application layer replication is already used by very large and very well-known distributed systems like Redis, like Postgres. In fact, that log concept that we use for our to-do list app is known as the write-ahead log or wall for Postgres. So if we can just figure out a way to apply these techniques to any process or any VM, then we can migrate anything, anywhere. And that's exactly what we're going to do. And to do that, let's start by taking a look at the life cycle of a modern live migration, right? Like what GCP does when you're moving between availability zones. And we can actually split this live migration into 3 distinct stages. First, there's the pre-copy stage. This is what happens before any sort of migration occurs. Let's think back to our to-do list example, and let's imagine that we have a really big to-do list, like hundreds of gigabytes in size. There's no way we're going to be able to instantly copy all of that data over to the other node. It's going to take some time. So that means our VM is still and so what this stage is responsible for is copying the memory for our virtual machine to the new node without interrupting the existing running workload. So if our VM is still modifying its memory and running the application, our hypervisor has to be able to track those changes, same as how our log file was tracking changes, right? And we're going to send those dirty chunks of data to the other host asynchronously. But that's the catch. Because there's a delay between our VM actually changing the data and us sending it, the data on the other host is always out of date. Not all of it, of course, right? But as a whole, we have to consider it to be out of date. And remember, we were able to avoid this problem in our to-do list application because we'd wait for every write to be replicated to the other host. But in reality, it's got to be done asynchronously. So we have some of the VM state on the other host, maybe even most of it, but definitely not all of it, and it's not up to date. So that's where our next big step comes into play. The stop and copy phase. And the thing about VMs is that they're not really deterministic, right? So they're not guaranteed to react the same way given the same inputs. If we run the VM in 2 places at the same time, they're going to diverge. Imagine that they have a random number generator running in them, right? So we can't run them in 2 places at the same time. They're either running here or they're running there. Inherently, this means that we need to stop the VM on host A and then somehow start it on host B. But remember, as long as the VM is running on host A, we can't have all of its state available on host B. It's going to be out of date. So we have to stop on host A, copy the data that's out of date, and then we'll have the full state on host B and we can start our VM back there. That's the copy phase, and it's the key issue. It's the reason that live migrations are generally not zero downtime. There's an unknown amount of data that we have to copy after stopping your VM. So your VM's not running while we're doing the copying. And now it makes sense why live migrations fail when your application is under high load. It's generating so much data that it takes too long to copy it while your VM is stopped. And now the latency and bandwidth requirements make sense. Your node needs to be close to each other so that, we can actually copy everything quickly. So how can we mitigate these issues? These are kind of really problematic. Well, that's where our last phase comes in, the post-copy phase. And the idea here is actually really smart. When we stop the VM on host A during the stop and copy phase, we know there's a bunch of data that we need to send over to the other host. That's the cause of all of our downtime. But what happens if we just don't send the dirty memory? What if instead we send the minimum amount of information required to start the VM back up? So we send the CPU state, the process registers, all that stuff, but we don't send the memory. Well, in that case, the VM will actually resume just fine. But when it starts running, it's going to ask for the memory that we didn't send over. And we can't serve it the old out-of-date memory we might have available locally. That's going to break things. What we can do is go and fetch the dirty memory from the original host on demand. So our VM starts up and it attempts to read a memory region. We intercept that read request and go and fetch the data from the remote host. The main benefit of all this is, of course, that we no longer need to stop the VM for very long, just long enough to send the CPU state, which is really small. Unfortunately, this benefit is largely overshadowed by how latency sensitive is. So imagine your app tries to access a variable on the stack and it takes 100 milliseconds to do the lookup because we're fetching from the underlying memory, right? So a big reason for all of this is that and a big reason for this latency sensitivity is that the most common implementations of this phase just suck. Most hypervisors, QEMU for example, intercept the read request for that memory through a kernel feature called user_fault_fd. And the way user_fault_fd works is both clever and very slow. You basically register a memory region, a chunk of memory with the Linux kernel, right? And tell it that for the first read on each page in that memory region, we should trigger a page fault. And instead of the Linux kernel going and fetching that page fault, you want a user space program to respond with the data. So my VM tries to read the memory region that I've registered with user_fault_fd. That triggers a page fault, right? And my user space program responds to that page fault with the correct data. As it turns out, this process is really slow. You start in user space, your request goes down to the Linux kernel, that's a context switch, then back up to user space where we respond to that request, then back down to the Linux kernel, and finally back up to user space. And because we have to do this for every single page fault, 4 kilobytes at a time, and because we can only do this single-threaded, it takes a really long time. Now, we did try and make this process faster. We actually wrote an open source user fault library for Golang, and we did actually come up with some really interesting techniques for increasing the throughput by a lot. But ultimately, we found a much better solution. Okay, so let's talk about our magical better solution. And as part of that, let's begin by defining some very rough goals for ourselves, right? We're going to try and get this idea of zero downtime live migration. And because we've talked a lot about the problems that have historically made this impossible, our solution has to solve all of them. So our first goal is that we want our solution to be hypervisor agnostic. We actually picked Firecracker for this reason. Not only is it open source, but it doesn't provide any sort of support for live migration, so it was the perfect candidate. This is also going to become important later because eventually we want to not require a hypervisor at all. We want our technique to be able to work on any process anywhere, regardless of if it's even virtualized at all. So this way we can guarantee that our technique is going to be portable. Next, we want to enable zero downtime live migrations, even when the application is under heavy load. So if our app is generating a bunch of data, we want our migrations to be basically instantaneous with no downtime. And we want it to work in environments that historically can't even come close to supporting migrations, environments with high latency or low bandwidth. We still want this to work. And we mentioned that we want to be able to migrate the data for our VM as well. I mentioned this before during the to-do application that the VM live migration requires that you're able to mount the same storage on both nodes. And that's just not practical. Try mounting the same volume on GCP and on an on-premise VM and an EC2 instance. The magical low latency infrastructure for this just isn't possible. Okay, so our solution has to somehow migrate the data volume that your VM is using. So we got to somehow, live migrate your EBS data on EC2 along with the VM itself, right? And we want this thing to scale, right? So we want to find ourselves in a position where we can move fleets of VMs around concurrently. And a good way to do that is actually just have the migrations be peer-to-peer. And finally, and arguably the most important piece of the puzzle, we want to migrate network connections as well. And I mean arbitrary TCP or UDP connections around the world between cloud providers. That's a hard requirement. And now that we have our requirements, let's go and implement it. And we'll start with the pre-copy phase. Remember that the pre-copy phase is traditionally used to track changes for your VM's memory so that we can asynchronously send it to host B, so that we have less to move later, right? We're just trying to amortize our migration time. And for us, there's two pieces we need to look at. One, this is something your hypervisor normally has to support out of the gate. Like we said before, usually that's implemented by user_fault_fd, right? That's how QEMU does it. But we want to be hypervisor agnostic. And with Firecracker, which is what we're going to start with, well, it can create snapshots, and in fact, it can even track dirty memory to create smaller snapshots of just the memory that's changed, but it has to pause the VM every time you want to take a snapshot, which can take tens of seconds. So your VM has to be paused for tens of seconds continuously, right? So this existing capability, while interesting, doesn't really help us for live migration. And the second thing that we're going to have to keep in mind is that we don't just want to move the VM memory. We also want to be able to move the VM's data around. Okay, so with those in mind, what do? Well, our key requirement is pretty straightforward. We just somehow need to track the VM's memory and its disk. And we want to be able to see the writes as they come in, right? And usually, like we said, we do something with we use something like user_fault_fd, but that's not fast enough. But what about block devices? If we could somehow create a block device which services your reads and writes via a user space program or user space program, we'd be able to easily intercept all reads and writes on that block device. And it turns out there's already a Linux kernel module that sort of allows you to do this, and it's called NBD. The way NBD works is actually quite simple. It begins with two pieces, the NBD Linux kernel module, which is part of the mainline Linux kernel, and the user space program that we implement. First, they establish a connection between each other, either over a Linux socket or a TCP connection. Next, the kernel module can create a block device that exposes it to the and expose that to the Linux operating system, usually at a path like /dev/nbdx, Now, whenever a read request or a write request goes to the block device, the kernel module just sends it to our user space program, which is free to respond however it wants. In our case, all our user space program needs to do is keep track of what chunks of data are being written to. It doesn't even need to know the contents of the data. It can just forward those operations to the real disk, but it just needs to keep a manifest of all the blocks that are dirty. That way, it can sync the data to a remote system asynchronously. And with this, we can create data volumes for our VMs that are backed by EBS or normal hard drives because we're just going to forward the I/O to them. But we'll be able to do the pre-copy phase for our VM's data volumes because we can see the writes. On top of that, if we can just convince Firecracker to somehow write the VM's dirty memory to another one of these block devices, we'll be able to use this technique for our VM's memory as well. So how do we get Firecracker to write the VM's memory to a block device? Well, we're going to, again, rely on the Linux kernel because, we want this to be as hypervisor agnostic as possible. On Linux, you can use the mmap syscall to map a file on disk to a virtual memory region. And you can see in the function signature there that it accepts a file descriptor. That function will return a buffer and its contents will be the file of the disk. Reads to those memory regions will be serviced by the underlying disk. Now, here's where it gets interesting. If you pass the map shared flag during that syscall, the Linux kernel will track writes to that memory region and asynchronously write them back to the underlying file. So if that file happened to be on a block device, whenever the Linux kernel decided to flush those changes to disk, they would appear to our block device as writes. And all of this is asynchronous and extremely performant because all the scheduling is done completely in the Linux kernel. So our patch is actually kind of simple. In fact, the total patch that we made to Firecracker is about 100 lines. Okay, so that's all helpful for the pre-copy step, but how about the stop and copy part? We still need to pause the VM on host A, copy all the data that's out of date, and then resume it on host B, right? Well, right off the bat, we gotta get rid of the copy all the data part. One of our goals is to have zero downtime migrations, and if we're gonna be copying data around while the VM is paused, we are not gonna be able to achieve that. So we're actually going to rename this phase to the stop and start phase. And during this phase, we're going to move the bare minimum amount of data. Remember how our block device was keeping track of all the dirty chunks of data? Well, during this phase, we're going to only send our CPU state, the process registers, and a manifest of all the dirty chunks that we haven't gotten around to moving yet. So we're not just sending the data itself, right? We're not going to send that at all during this step. We're just going to send a list of what we don't have on the other host yet. And just like before, when our VM resumes on the other host, it's going to try and access that data. And this is where we can actually take advantage of post-copy migration for the first time. When the VM tries to access its memory in our situation, or its disk, remember we're going to be handling that too now, we don't need to go through user fault FD anymore for both the VM memory and the disk. We'll just run more of our user space block devices on the new host for the VM memory, which we're still going to mmap, and for the disk. And we can pass our block devices directly to the VM. Right? So all I/O will go to our user space program via the block device. And if we have the data being requested available locally, we can return it right away. And if we don't, we'll just go and fetch it from the remote host. But now we're not limited to a single thread. We can pull data as quickly as possible in the background. There's very little context switching, and we're not forced to handle just 4 kilobytes at a time. And with that, we've actually reached our destination. Architect is a culmination of all of the work that we've done, and it's an orchestration framework and control plane that enables existing orchestrators like Kubernetes to perform zero downtime live migrations for any stateful workload. And it does so by managing 3 projects. Silo, which is responsible for migrating the storage, and so this means the block devices that we were talking about. Then there's Drafter, which is responsible for the compute, so that means interfacing with Firecracker, as well as handling the migration of user space processes, because we actually have opened the door to that. And finally, there's Link, which is our global networking layer, and it's responsible for migrating the network connections around, right? It's able to migrate arbitrary TCP and UDP connections. This is actually a really cool piece of technology, and it could be a talk on its own. I don't have the time to talk about how it works, but It's able to keep the network connections live during the migrations. Clients don't notice that the migration has happened, and you don't need to reestablish any new connections. Things just keep working on the existing, already established TCP and UDP connections. Now, Drafter is already open source, and it contains actually enough of Architect's Orchestrator that you can do these migrations locally. We're going to be open sourcing the other ones at some point as well. Silo, we're almost ready to do. We're just pushing the finishing touches on it now. Okay, so all of this sounds great in theory, but how much better is Architect in reality? It turns out a lot. One of our engineers, Felicitas Postinger, actually did her bachelor's thesis on this approach, and she very meticulously benchmarked all of our different methodologies, user fault, the block devices, everything. We're going to go through these benchmarks in a moment, but if you'd like to check out the paper that she published, which is peer-reviewed, here's the link for that. Okay, so here we're taking a look at the latency to fetch the first chunk of dirty data for a VM. And we're looking at how the first chunk latency is affected as we increase the round trip time between our nodes, right? So there's 3 different benchmarks that we're doing here. We're first looking at user fault FD. That's the blue diagonal line. Then we're looking at direct mounts. And direct mounts are basically, we're using a block device, but we're going to go and fetch the data as it's being requested. We're not going to do any work in the background, right? And then the last benchmark here, that's the special one. That's the post copy implementation, right? We're not limited to 4 kilobytes at a time anymore, and we are allowed to move data in the background. So we do go and do that with the green benchmark, the managed mount. And so, as you can see, latency is significantly better than even user fault FD, even as the round trip time grows. Okay, latency is cool, but how about read throughput? How much data can we read at a time? In short, a lot more than user fault FD, right? In this benchmark, we're competing the read throughput of our various different approaches to the network round trip time, right? Even when the round trip time is 0, our block device approach has a much better throughput than user fault FD, which drops to 0 as soon as we start adding any sort of latency. But our managed approach is able to maintain a much better throughput because it's pulling data in the background. Okay, how about write throughput? As expected, our block device does better in that scenario as well, especially as RTT increases. And now we're at the point where I think everybody is waiting for, a live demo. I've gone ahead and spun up 3 nodes around the world for us today on different cloud providers. We have a node in Frankfurt running on Civo Cloud naturally, then, because we're trying to make Architect work literally anywhere to anywhere, we actually have an on-premise server in New York, and this is just basic co-location. And finally, I have an AWS box in Dallas, and we're going to be actually doing various migrations between all of these, and the client is going to stay alive. It's going to be my laptop here in Austin, and very soon, your laptops when we do the Minecraft demo, if you guys download that. But first, let's start by moving Redis around. Okay, so for the Redis demo, we need a way to visualize the latency to a Redis instance. So we've put together a really simple application, and all it does is plot the latency for set and get operations to a Redis instance. It does not handle any sort of reconnects. It's just an off-the-shelf Redis client library, super simple application. Okay, so I'm going to move this way. There we go. A terminal here. There we go. It's going to be a little bit hard to see. Oh, there we go. It's easier. Oh, do I have internet? Maybe. Oh, yeah, I do. Okay, cool. So I'm going to go and I'm going to start the connections. I just want to be able to show the logs. That's really all this is for. As you can see, I was testing some stuff before. Okay, cool. All right, we should be in a spot where we can go in and start our little application for seeing the latency, right? Which we call latency. Really clever name, I know. Okay, and we're just going to type in our tect.run. Okay, great. We're going to set our interval to 50 milliseconds. I'll explain what that is in a second. Okay, now you need to actually go and deploy Redis really quickly. So I'm going to apply. And if we go back to our logs, we should see that there's a bunch of stuff happening in the background. Cool. All right. Now we should be able to connect to our Redis instance. Okay. So our Redis instance is running on a Civo, a machine in Frankfurt. And we can actually see that here. Right here. Are you gonna let me? Okay, good. This is really hard to do, looking backwards. Okay, cool. So you can see that we're running on a Civo machine in Frankfurt, right? We're going to trigger a migration in a second, but first let's start by hitting our Redis instance. Let's start the test. All right, there we go. All right, cool. All right, so it took more than a second to establish the connection, but we flattened out about 200 to 270 milliseconds of latency from my laptop over a hotspot. I know, over a hotspot, but over a hotspot to Frankfurt. Okay, and now we're gonna actually move this to the on-premise server in New York. So let's start by doing that one first. Okay, so I'm gonna go. No. Cool. And this is the name of our node in, and this is just a Kubernetes YAML to be clear, right? The name of the node there is on-prem NYC and NYC, New York City. There we go. And we're gonna just apply that. Cool. All right. So you can see that we've moved into the migrating stage. We're starting to pull the data in the background. Obviously, everything's still working. You can ignore that latency. That's just the hotspot being weird. And right there, the migration just triggered. And we see a very interesting shape in our graph, right? Not only have we actually moved the instance, right? This was our stop and copy phase that we're seeing here. That's the spike that we're seeing here. And we're moving the data, we're reconfiguring the global network, we're doing all of those things. But without reestablishing the network connection, we actually saw a lower latency. And we got that because we've actually migrated closer, right? We moved from Frankfurt to New York, which is closer to Austin, and so we see lower latency. Now let's actually move it even closer. Let's move it to Dallas on AWS. So again, we're going across cloud providers, across physical machines. I really wish I could do this faster. There we go. Okay, and this is, what do we call it? AWS Dallas. Cool. We're going to go back into our migrating state. You're going to see the other machine start to pull the data, and you can see we saw the exact same shape again, right? Except it's even lower because naturally, Dallas is closer. Okay, so this was cool. Let's go back into our presentation for a second. Okay, so that was pretty cool, but we could have totally faked it, right? The client is running on my laptop. We could have modified the protocol to look like it was migrating. It could all be smoke and mirrors. But you know what protocol we can't modify? Minecraft, especially if folks in the audience have downloaded the official Minecraft client and are connecting to our server during the demo. So please connect to that Minecraft server. I'm going to start it in a second. You'll see me start it. I'm going to do the same thing on my laptop here. And the URL for the server is minecraft.architect.run. And please make sure you're using client version 1.12.2. That's the server that we're running right now. Okay. Let's go back here. Okay, cool. Let's go ahead and delete Redis. Don't need that anymore. Cool. Awesome. Okay, I'm almost done. Okay, so now I'm just gonna go and Minecraft should be quick. Good. Should get started pretty quickly. Great, we should be running Minecraft. Now why don't I move the Minecraft client over to this new screen? Great. And it has decided to put me in the middle of the ocean. Of course it has. Okay, well, this doesn't really affect the demo at all. But you can see, we've connected to Minecraft. It's running here. And because I'm a little bit short on time, I'm actually going to move it directly to Dallas. Okay. So let's go here to our kubectl. Let's do that so we can see nano Minecraft multi. Great. We're just going to use the same node name as before. Okay, and we're just going to, just like before, we're just going to call kubectl apply dash Minecraft multi. We'll move it to the migrating state. begin pulling the data. Now, this is actually really interesting, and this is kind of why I wanted to skip the other one. Turns out the latency between the nodes in Frankfurt and the node in Dallas is really low. Okay, so the latency is really high and the bandwidth is really low. So you can see that the migration is taking a while. Now, this is problematic for the demo and can take a few seconds, up to a minute or two. But in return, we get to show off that the migration works just fine, even on high latency and low bandwidth networks, right? That is mighty slow today. 5.4 megabytes per second, good lord. Well, great, I drowned. But as you can see, like, you know, during the migration, everything is working just fine. How should we do this? I guess we can just wait. It's going to take about another 50 milliseconds. I'll go to LAN in the meantime and start breaking blocks. Not really sure why it keeps choosing to put me in the middle of the ocean. It's funny because I was doing these demos last night, just kind of testing to make sure they're working, and it was fine. And then as soon as I tested it this morning, for whatever reason, the server just decided you're always going to be here. Okay, so we're about halfway done. I don't really have much to say after this, so we're not gonna. It's not gonna take much longer. Oh, shoot. Okay. Okay. Well, why don't I go and just finish my talk in the meantime? Yeah. Where's my mouse? Oh, there it is. Oh, we're actually almost done. Oh, the bandwidth must have gone out. Okay, cool. All right. I guess we'll finish it here. So okay, so you can see, we're breaking blocks, things are happening, and everything just works just fine, right? And so even a protocol like Minecraft that we can't really control, that we can't really modify, live migration still works just fine, right? Okay. 30 seconds. Okay. Okay, everything worked. We were able to keep our original promise from anywhere to anywhere and any application, right? Stateful workloads on spot instances are now a reality, and we can do that today using Architect. You can do multi-cloud, there's no more vendor lock-in, there's no more cloud lock-in, and in fact, because this works fine with on-premise infrastructure, you can actually have hybrid deployments where the cloud is an extension of your on-premise compute. Pretty far, and we can actually go pretty far with our future work on this, right? We've moved a Firecracker VM around, not a container, and in the future, we're actually going to be able to migrate arbitrary Linux processes in user space using the same technique, right? That's going to open up a whole new set of doors for us, like migrating workloads from VMware to EC2 instances without downtime. We're also working on moving NVIDIA GPUs around, but you're going to have to wait a little bit longer before I can show that off. Okay, and with that, we're done, okay? Thank you for sticking with me until the end.